Hi there, my name is Ian McTavish, and I'm the programming mentor for Team 4152, Hoya Robotics, and this is our tutorial on Introduction to Programming for FRC. The slideshow for this is located at bit.ly/team4152 programming, and note the capitals. T and P have to be capitalized so that you can access all the links in the slideshow for this. So before I begin, I do need to thank all of our sponsors. All of our sponsors have contributed to our team and allowed us to really improve over the last couple of years. So a big thank you to them and to our supporters. The other person I have to thank is Oliver Bile. The code that you're going to see in this, Oliver Bile has developed, and he's been our programming mentor, our programming student for the last 2 years. He's also been our team captain, and he's really elevated the programming quality for our team. So let's get started. So the goal for this tutorial is this is for kind of anybody. Obviously, if you're brand new, you're going to kind of get an overview for this, but we also have some tips that hopefully we'll find more experienced programmers will find useful. But to begin with, for our team, we use the Java programming language, and the best way to learn this, in our opinion, is to take our ICS3U computer science course. That's the one that I teach, and that is a shameless plug. Other resources, there are a plethora of resources out there on the web. The reason I've put down the W3 schools is I like the layout of it. You don't have to have a subscription. You can just go to their page and learn it, and I've got a link to it there. It's very important to understand that Java is a different language from JavaScript. So there's a lot of resources out there for both languages, and it's making sure that you understand the difference. The other one is the University of Waterloo has an amazing set of courseware, and they do have a course that's all in Python, but they also have one that the goal for it is that it's not specific to any programming language. So understanding things like loops and variables and methods, these are all kind of core concepts of programming languages, and that's a great course. It's free, it's online, it's easy to access. The last thing is Replit, and Replit is basically a website where you can start programming Java. We find in our board, Chromebooks have really taken over, and it becomes an issue when students can't install software. So Replit is web-based, which allows anybody to be able to start programming Java very quickly, very easily. Now, a key thing is programming for robotics. There's a connection between what you are writing in code and what the physical hardware is. So the WPI library, there's fantastic resources on understanding the control system. This is kind of required reading for our team if you want to be involved in programming or electronics, and you should take the time to understand how everything goes together. So this is just an image of kind of the base drive base. You have the RoboRio here, and you have the Wi-Fi router, and so these things are connected, and you have your motor controllers, and so at the very least you are sending a signal to the Wi-Fi router, which is getting interpreted by the RoboRio, which is then sending a signal to the motor controllers, which will then start turning the motors. So that's the very basis, but how things are wired really depends on what you're communicating with and how you're setting things up. So take some time to read through that. This is just an example of the page, and you can see they've got all kinds of information about programming. They have information about all the different software, the hardware, and this is really key, is how to get everything installed and set up. A guide. Installing LabVIEW, that's another programming language for that some teams use. The different game tools, how to wire a robot, how to image your RoboRio. So this is all software that Your RoboRio is basically a Linux computer, so it needs to be set up so that you can run it properly. How to program your radio, this is a really important step, and how everything kind of works. So there's a ton of information, and it's worthwhile to go through. So there is another page here, and this kind of goes over the different components. So for example, the RoboRio, when you go to competition, it has to have a certain image with it. So it's being able to understand how to set up the RoboRio so that it's up to date. The Wi-Fi router needs to be configured differently. I cannot tell you how many times I myself and other teams come back from competition. They go to use the robot, they can't. And it's just simple. They need to configure their Wi-Fi router so that it will work, because it gets set up for competition mode, and that's different from when you're at home. So it's making sure that you understand those things. And just some things for our team, I really want us to focus on using Smart Dashboard and Shuffleboard and Live Window. Basically, the idea is that as we're running code, these are tools that you can have values being shared with the driver or the coach who's looking at the screen, and that can be a really useful troubleshooting technique. The other key piece of thing is Visual Studio Code. So this is software that we use to program our code and then deploy it to the robot. So we use a Windows machine for this, and it's really important to get a handle on how to use this so that you can get code operational. Now, let's get into the nitty-gritty. So we have a GitHub page, and Hoya Robotics is our team name, and we keep our code up here. We make it public so that other people can explore it and learn from it, and because we've learned from so many other teams along the way, so it makes it hopefully everybody can keep improving by doing that. The other thing is that it allows us to keep our files synced. We have two different programming laptops so that we always have a backup, and we want to make sure that we can have the code on one, and then if we're making changes, we can sync it with GitHub to make sure everything's up to date. So this is the link that takes us to our code for the Infinite Recharge season from 2020. And we have a whole bunch of different folders here and a different number of files. And the key thing is that we've, Oliver, who is our programming lead, did a great job of taking time to really structure his code. And our hope is in the future we'll be able to build on that structure every year. So the first file, this is the starting point. This is the Main.java file. And basically with the Java programming language, every program has a main method, and that's where everything starts. And you'll notice I put a little asterisk in there. There are people that are programmers that will go, well, you don't technically need a main method, and that is true, but you'll find the majority of Java programs tend to have a main method. It's a kind of a standard. You can configure your compiler to have a different thing, but at the end of the day, it's good to kind of stick with standards. So this is where our program starts. Here's the main method, and we're going to look at it. You'll notice that in our main method we have public static void. So these are all keywords, and I'm not going into there because that's the whole goal of taking a computer science course or learning using some of the resources that I mentioned earlier. So there's the main method, and then the arguments for the main method are here, and there's a squiggly brace. So in Java, you have squiggly braces to define where a block of code starts and where a block of code stops. Many programming languages use this convention. You will notice some, like Python, for example, uses indented lines instead. So it's important to understand the language that you're using. So the squiggly brace starts and stops our code. You'll notice our code is one line. And basically, we're going to take the robot base and the start robot method, and we're going to create a new robot. That's it. So all of the code is in separate files, and we're going to go over that. And anything that says robot, so we would look for the Robot.java file to find the code for it. And we're going to be looking at that in a moment. So a Java file, there's a couple key aspects to how it's structured. So I'm trying to highlight a few things. Number one, when we are creating code, we package it. And so basically we've got a lot of different files. If you think of a video game, you would have a video game where you would have files for code. So you would have code that is specific to the boss, specific to the player, specific to the controllers, all of those kinds of things. And so you package them. So everything that is part of that package, and in our case it's FRC.robot, it goes through all the files, finds those packages, and incorporates it. So when you set up initially, you'll be creating your package name. Also, we are importing different libraries. So there are libraries of code that already exist, and even though you could create it all from scratch, it's really important to take advantage of the resources that are out there. So the WPI, they create a lot of the code for FIRST robotics that a lot of teams use, and basically they have a robot base, so we're just importing that and using that kind of as a template, so then we can customize built on that. The other thing is we are using object-oriented programming. So in object-oriented programming, you're going to see classes. And classes are kind of like blueprints. So the idea is that you would have a class, and I'm going back to the video game analogy. So for the player, you would have a player class. And all the code that relates to the player, so maybe the code that takes the joystick input to decide where the player moves, that's all incorporated into that class. So we have a main class, and then again, squiggly braces. So this starts it, and down here, that ends it. And so every time you have an opening, you have a closing. So we have our different methods, and then there's our main method, and that's what we're going to start exploring. So we have a bunch of different files in the main robot folder. One of them is called Constants. So the idea for us is that we found in the past, we ran into issues where we would have different, let's say we had code to be able to handle things from the joystick and stuff. And we would have issues, different spots where it referred to it, so we'd have to name it. Well, what we do is we keep a constants folder, so everything is here. So for example, we decided that the left joystick on the Xbox controller is how our driver is going to drive. So in here we have a variable that references that. Every time we use in code, we just simply use the refer to this, and it's always set to the left joystick. If we have a new right driver that goes, oh, I really want to use the other joystick, well, we can change it here in one spot, and it will change it for the entire robot, every single spot we refer to it. So it gives us a way to set values in one spot, and we can make changes really quickly and easily that will impact the rest of the program. So obviously there's the driver controls, but there's other controls in there as well. So the other thing is we have a robot class. So the Robot.java file, you'll notice that it extends the time robot. I'm going to show you that in a moment. But basically, remember, we're importing from the WPI libraries, and so they have a timed robot. And the framework for the timed robot is that there's a series of loops. So basically, here's one right here. There's a robot init. So when the robot starts, this code runs. And then once that's done, then it goes to the next thing and stuff like that. So there's the robot periodic. So during the game, this method is constantly called. And what we do is in here, we are basically saying, okay, in the robot initialization, we're going to create a new robot container, and we'll look at that code in a bit. And then we're going to just log that information. So the robot is started. This allows us to go through our logs later on and double check that, and this is custom code. I'll be showing that to you later as well. Robot periodic, you'll notice that we're looking at how many milliseconds have passed, and basically we're just doing a double check. This is a really important thing to keep in mind. When you set a series of code, so let's say, for example, you want to have the robot move 20 feet. So if you have code where you're going to loop and you're going to go drive 1 foot, and then the loop goes and you drive another foot and you drive another foot. The problem is that over the time it takes 20 feet, it takes a couple of seconds. Well, nothing else can run in that because your loop is constantly running for that 20 seconds. So a different way to do that is you say, set the motors on, and let's record the time, and let's record where we are right now. And then in the robot periodic, you're checking the time update and you're checking the position of the robot. And once the robot's past 20 feet, you turn the motors off. That way, all the other code can be functioning as well. So you can kind of override what the robot is doing and get code to happen. So this is the timed robot class, and the reason I'm showing this is because it's really important to read the documentation. So the WPI libraries, they have documentation, and it seems confusing at first, but as you start using programs, always take the time to go, okay, I see this and I don't understand what it is, and so go look it up, and you can see, okay, this is all the different things. It inherits robot base, it inherits iterative robot base, and down here it explains what it does, and then there's the methods and everything. And it's really important to do this so that you understand the core programming that is behind everything, so that you can refer to it and build on it. So RobotContainer.java, basically this is where we have all of our commands get set within this program, and I'll be explaining how commands work and everything, and our autonomous code. We're going to go over the autonomous code right now. So here's our autonomous code. Unfortunately, I was using a YouTube video of our match, which was kind of grainy, but this is our robot right here, Team 4152. This is at Georgian College last spring. And this is our autonomous code. So at the beginning of the match, we are using a command structure in our program. So we're getting the autonomous command, and this is what we're doing. We're returning this news. So the first thing is sequential command group. So it's going to go through all the commands sequentially, one after the other. So the first command is to open the ball gate. So in our shooter, we have what we call a ball gate, and basically it's a little piece of Lexan that the purpose of it is to block the ball from going into the shooter, so that when we want to be able to shoot, we open the ball gate so that the ball can go through, and when we don't want to shoot, we block the ball. So it's just controlled by a pneumatic piston, but we've tried to use commands that are very clear. So it's open ball gate, so we can find the code in our program to open the ball gate and see how that works. So the next one is a parallel set. So what happens here is that these two commands are going to happen at the same time. So the first one is turn the turret for a time. So when we start, our turret has to be facing away from there. That's to keep it within our robot perimeter. So the first thing that we do is this turret starts turning, and as it's turning, we're going to drive for time. And you get points for moving off of this line. So we found that we did a lot of testing and found it was just as easy to do time to move to this position, and it was incredibly consistent. The way our shooting was set up, we could get incredible accuracy for shooting. So it worked really well for us. The issue with time is that it depends on a lot of different factors. So because we're moving on a smooth surface, this works well. If we were doing a lot of maneuvering, then we might want to use the encoder values so that we can read how far our wheels are actually turning. There's a lot of different techniques that can be used, and the goal for us was we wanted a really consistent, we could always get 3 power cells in our autonomous mode, and we did enough testing to know that this worked consistently well for us. So we are now in position. Our turret is now being turned, and so our next stage is our align turret and our shooter rev. And so these steps, basically what happens is that the align turret, this is our codes that we use for shooting. And so in the teleop, basically we look for when the driver presses a button, and it simply is running the same code. And basically the align turret, what it will do is it will use our camera to recognize the target. It will automatically turn the turret to face the target. It will calculate the distance from the target to the robot, and it will set the speeds of the wheels, which is then used in the shooter rev, and it will set the speed so that the speed will be the perfect speed to get the balls into the target. This was done by testing. We did about 1,000 shots in testing to calculate the correct speeds for different distances and everything. So it's really important to spend that time testing your code to make sure that you've got that information. So basically, we're now at the point where the timed intake starts. So our storage system has polycord belts, and this starts pulling the ball up into the shooter, and the ball shoots out. You can see the ball right there. And immediately we start up the rev again, which will then get the wheels up to speed. And once the wheels are at speed, it'll do our second timed intake. So there's our second ball that we've shot. Again, rev up the wheels, and then do our third intake and shoot it. So that was our autonomous. It worked really well. We got 3 power cells in every time. It was not perfect. We had plans to then move and pick up balls and shoot the balls, and the problem is we ran out of testing time. We wanted to guarantee we could get those 3 balls, which we were able to do, but to do that, we had to put a lot of time into that, and we ran into the testing. So the key thing is, now that it's the off season, now we're working on that so that we can develop those skills. So in future years, we'll be able to do those kinds of things effectively and move into using motion profiling and things like that. So there's a lot of things that you can do. It's just putting the time in to learn it. The next key thing is that we found that after the autonomous, our driver would then take over, and in teleop would move into this position and intake the balls. And you can see our intake is still up. So this, according to our video play-by-play afterwards, it took an average of 10 seconds for us to get that intake down to be able to suck up the ball. So after our Georgian competition, we decided that's ridiculous. Let's add that in the autonomous mode so that we're ready to go. So we added a command so that this would set raised for the intake to false, which means that it drops down, it's pneumatic controlled, and it would be able to suck in the ball. And by shaving time off, our goal was to be able to have the driver ready to pick up balls faster so that we can get more points. The other thing that I want to mention is that with GitHub, you can see all of those changes. So you can see that we added, on June 8th, we added our updates from the Georgian College. We had those done right after March break, but we ran into the coronavirus shutdown that everybody kind of ran into, so we didn't have access to things to be able to post our updates there. But you can see everything that happens, and commenting stuff is really crucial so you understand. And in GitHub, the nice thing is that it shows you what code was changed. So every time we change code, we automatically update it to GitHub, and we can see, oh, we deleted this line, and the green indicates we added these 2 lines. The bonus for this is that if we find that something really screws up, we can roll back to a known good situation and then examine what code was changed that caused our issues. There's also some other folders in our code. We have 3 folders: commands, subsystems, and util. I'm just going to explain how we structure them. So in the commands group, we have different files for all of the different, I'm going to call them verbs. So with object-oriented programming, we find it really helpful to kind of write out our robot requirements. So what do we want to be able to do? Well, we want to be able to, in autonomous, we want to be able to drive for a set amount of time. So anything that we kind of write down that's a verb. So drive is a verb. Then we look at creating a Java file for it that will encapsulate all of the steps for that particular thing. So obviously we needed to be able to shoot ball, so we built that in. And some goals of object-oriented programming is to kind of separate things. So for example, shoot with trigger, in the teleop, the driver wants to be able to press a button to shoot the ball. And in autonomous, we want the robot to be able to shoot the ball without the driver. So we have shoot ball, but we also have shoot with trigger, which basically says, okay, when this button is pressed, run the shoot ball file. So that way we can keep all of our logic organized in the proper structure. So in future years, so I'm going to use, for example, there was first first Steamworks, for example. So in first Steamworks, the robot had to be able to drive around the field, and it had to be able to pick up gears and deliver gears. So we would create a file called pickup gear and another file called deliver gear. And those commands would be run. So if the driver pressed this button, that means that it's delivering the gear. And sometimes it's not based on the driver, it's based on, oh, the sensor indicates that we're in position to deliver the gear, so it will run that code. So that's kind of how we structure things. We also have another folder called Subsystems. And so I've mentioned the commands are based on verbs, so these are nouns. So when we're doing our analysis and our robot requirements, we decide we're going to have different subsystems. So this year, we decided that, okay, we were going to have an intake that we could intake balls. We would have a shooter that would be able to deliver the balls. We would have a drive base, and pretty much every year we always have a drive base. We're going to have a limelight camera, which allows us to identify the target using vision. We would have a climber that could climb the ladder. And so all of the different things that we incorporated on our robot are in there. So all of these subsystems have their own code, and they relate to each other. So shooter.java, for example, has an isStable method. And the whole purpose of that is to check, and we identified we could determine where our ball would land based on the RPM, the revolutions per minute, of our shooter. And so we decided, okay, the key thing for that is how accurate that is. So isStable will check for 400 milliseconds and determine the highest and lowest speed. And if it's within a certain range, then we can reliably say that the shooter is going this fast, which means the ball is going to go this distance. And so in our commands, we have a shooter rev command that calls that method and checks. So if it's at the appropriate speed, it will start the sequence to shoot the ball. And if it's not at the appropriate speed, it calls it again. So waits 400 milliseconds and does it. And the whole point for this is to optimize that so that way we can do it as fast and effectively as possible. So thinking of things as nouns, what are the components of your robot, that helps. You'll notice we don't have our storage system. And basically our storage system is incorporated into the shooter and intake. We would probably separate those in the future because we found that was one area that we could improve our robot on. You can always improve. There's also a utilities folder, and so these are kind of helpful classes. So logger, for example, this is custom code that we've written, Oliver wrote, and the idea with the logger file is that it writes messages to a file. So we put a memory stick into our RoboReel, and this memory stick files get added to it, and then we can load up that file. So when we were doing our testing, we would do all kinds of testing, and then we would take the USB stick out and update our spreadsheet with all the values from it. So we would have a record of every single test that we wrote, and we would have a record of the variables from the code for every single test, and allowed us to identify problems with our code. So if the ball was going low, we would look at what was the RPM, what was that, and we were able to fine-tune it by using a spreadsheet and graphing it, and then figuring out what the proper quadratic equation that we would need, because we recognized there was a quadratic relationship to it. So it was really, really useful for us. So the logger file, basically keeping track of your code, and same thing for doing it in game competition and stuff. And the challenge is balancing it so that way your log is really effective for you and doesn't slow you down. Utils is another thing, and this is kind of just utility code that we found is useful. So we've always found that joysticks are not terribly precise. If you move it at all, you can start the robot, which sometimes it's too sensitive, so we employ a deadband. So basically this is just a quick function. What value are we getting from the joystick? If it's less than this amount, then we're just setting it to 0, just so that way we kind of have that deadband area. For vision, this was a kind of a bit of a game changer for us this past year, and I have to shout out to Cavalcade and Trillium Lakelands District School Board. We approached them about sponsorship and funding our team, and thanks to them, we incorporated vision into our robot. We got 2 Limelight cameras, which was phenomenal. And with the cameras, basically, the Limelights are really nice because they've got their own system, and it's pretty easy to use. But just go through the documentation and just follow it. And it worked really effectively for us to be able to add automated targeting to our robot, which we ended up winning the Industrial Design Award at Georgian College for, because of our autonomous targeting steps. Now I'm just going to show this video because I just want to explain some common things that we've come across over the years. So this is first power up, and there's our team over there, and our robot is actually in this corner here. So just watch this for a few seconds. So our robot in autonomous moves forward. We have to cross that line. Now you'll notice we kept going, and the issue is we were using Talon SRXs, which are great motor controllers, and the problem is that the Talons have different modes. They have brake mode and they have coast mode. So brake mode, basically the motor will start and it will run, and when you stop the motor, it will basically stop it really fast, and so you brake. Coast mode is it stops the motor, and the motor will just gradually slow down, allowing you to coast. So in that particular season, our programmers were setting everything up, and they were telling me that, oh no, we can't, like, the problem is that you can change the mode, but there's a physical thing that you have to do on the motor controller, and that was the thing. We can't use it in autonomous. We wanted brake mode so we could go to a specific spot and stop, and they said can't be done because then we're in brake mode for the rest of the match. And I challenged them on that. I'm like, are you sure? So again, time is the biggest barrier. We simply ran out of time, but after competition, we researched it and we looked it up, and sure enough, there's the user's guide, and reading through it, you can see that, oh, each programming language has a way to switch between them. So if you go into the documentation, there is the brake mode and the coast mode, and we just simply use the search command for it. And this is the key aspect that I want to emphasize, is you don't know what you don't know. So they were making an assumption, and the assumption was because they didn't read all of the documentation. So read the documentation. Everything is online. Use search functions. If you're using a book, read the index. But basically, use that documentation to figure these things out and learn from others. If they had just gone and looked at code from other teams, they would have probably seen, what does that do? Look it up and go, oh, they're switching to coast mode. So we would know that that's a possibility. Another thing, and this is a link to our deep space code. So this is our robot for deep space, and our first competition at Durham College, we would basically use our elevator mechanism to be able to deliver hatch panels and cargo into the different holes. And so our driver would use the right joystick to move this up and get it on. And another mentor, Sam, and myself were talking to them and going like, we got to implement something so that we can automate that. And we researched it and we found PID Control. And so for our next competition at North Bay, we were able to implement it. And the basic idea is that the driver would get into position and would press a button. And so that button would raise the elevator to this level. And so what it would do is it would start in the down position, and it would move up, and as it moved up, it would start off really fast, and then as it got closer, it would start slowing down. So this is the proportional part of PID control. So the farther away you are, the faster you are, the closer you are, the slower you are. And the other aspect is that it would use the integral, the I, and basically what it's doing is it's looking at the distance and doing calculations on the error. So the idea is that if you go up, if you overshoot, it will come back down, and it basically oscillates until it's oscillating at such a small amount that it looks incredibly steady. Our driver wasn't terribly thrilled with this, but after competition, he was sold. He just found it was incredibly effective, and now analyzing video of matches, it definitely increased the speed that we could deliver hatch panels and cargo, because when we were doing it manually, there was a lot of up and down and overshooting, and the machine can be much faster than a human. Now, the one aspect that I want to mention, we were able to do PID control going up. Going down became an issue, because the thing is that as you got closer to the bottom, you would slow down. Well, the thing is that you've got gravity working against you, or like trying to pull you down. So what would happen is that by slowing down as we would lose the momentum of gravity, and we would get to a point where it wasn't going all the way down, which would mess us up later. So we ended up just ditching PID control going down. It would slam down. We designed our robot to be able to take a lot of abuse, so it worked, but it is something that we need to incorporate in the future. So I hope this has been useful. You don't get to improve on coding until you actually do it. So take the time to read the manuals out there, the WPI library. Take time to do that. Practice. And I'm just going to mention tinkercad.com. If you can create a free account, they have Arduino circuits, and I love Arduino circuits. Make Code for Microsoft has the same idea for microbits and Lego robots. And the beauty of this is that as long as you have a web browser, so Chromebook, Windows, doesn't matter, you can do this kind of coding. And obviously, if you have the physical things like an Arduino or a microbit or a Lego robot, um, obviously you can do it. But really, physical computing is a different kettle of fish. There's a lot of stuff about computing out there, and it's really important that with physical computing, you have different things such as how are things wired, you have real world physics, and these things play into stuff. So actually doing those things and practicing them, and it makes a lot of sense. So take time to play with that. Read the code of others. So if you just Google FRC GitHub code, when I did that, Team 254, their code pops up. They're quite literally the best team in the league, and my apologies to other teams that are absolutely phenomenal, but they've consistently done phenomenal things, and learning from their code. So for example, their intake, the 1 year, they needed to determine if the cargo was in the robot, and so they would read the amperage of the motor controller. And so if the amperage was higher, that indicated that the motor was working harder, which meant that a ball was being sucked in. So there's little things like that are really useful. Chief Delphi has an incredible set of resources, and so highly encourage you to look through Chief Delphi. And the last thing is, there's lots of ways to do things. Our strategy works for us. It might not work for you, and that's okay. The key thing is that learn from other teams, learn from other programmers, be methodical in how you approach things. And that's the key thing. Take the time, because that's always been our biggest barrier, is that we have a tendency to procrastinate, just like a lot of teenagers do, and so we end up not implementing things because we just run out of time. So take the time and learn from others, and you'll be fine. Thank you very much, and have a great day.